So this is me. I come from Kipu Quantum. It's a German company, and I will talk a little bit about what we are doing there. I'm one of those lucky remote workers that I can work from Spain. So you will see there's some references to wine in Spain, and you will notice it on my accent as well. But essentially, the talk will be about Counterdiabatic protocols, which is the main, say, technology that we leverage at Kipu, and how we have been exploring the field of quantum machine learning. In particular, you will see that we have a pragmatic view, and essentially we have been seeing how quantum computers can actually enhance the machine learning pipelines that our customers are currently working on and running in production. So Kipu Quantum was founded in September 2022. We are based, the main offices are in Berlin. We are around 40 people there, and from there we are working with different industries, trying to actually solve really challenging problems that could potentially be production scale and that currently may not be able to solve in quantum hardware, but still we are running on quantum hardware. Our main focus is quantum hardware, so we can develop proof points for a future roadmap, the scaling of this technology, and that our customers can decide, essentially can see when this switch from classical to quantum will happen in the particular domain. So we are quite pragmatic in that sense. We focus in application specific. We don't try to come up with algorithms that work for all the cases or all the instances. We try to leverage, let's say, the particular nuances of each use case to benefit, let's say, our approach, and also we focus on specific hardware. So if we know a hardware is really good at solving some type of problems, we try to marry it to the needs of the use case and the hardware that will be the best performant one. And we essentially sit in the middle, trying to come up with the shallowest version of the circuits, whatever needs to be running on the hardware so that it's minimal in its expression. The idea is to come up with some evidences so that customers can come up with a clever roadmap for the future adoption. So Kipu is more or less divided like this. You will see that there is a heavy investment in our core technology, the compression algorithms that we leverage. And for that, we need to know a little bit about the hardware providers we work with. So the hardware, the specifics of the let's say, the manufacturing processes and everything that goes into actually building those hardware machines. And we do partner with the key, let's say, hardware providers in those different domains, but we also work with our customers so that we can bring in the domain and knowledge that they have. We have people that knows about these specific domains, but of course nobody better than the customer itself to know what are the differences, like the regulations, every different detail that could apply to their specific use case. So I'm located in the projects area where we are mostly working right now, but as you will see by the end of the presentation, we are already leveraging some services that can be used by a broader audience. So in order to also expand a little bit the exposure of our algorithms so that they can be benchmarked and you can actually come and talk to us about some particular cases that you found interesting for using our technology. So you will hear a little bit, if you go to the booth, you will hear us talk about digital compression, analog compression, and digital analog compression. So our compression algorithms work at the algorithmic level. That means that once we have come with a short description of the algorithm we want to run, we can either transpile it to a fully digital approach, go into a fully analog device, or leverage the two when possible. So combining the analog blocks with some digital operations. Essentially, once we have the algorithmic expression, it all boils down to efficiently translating this into operations in the machine. And one of the key features for these protocols is the adiabatic gauge potential. So the family, let's say, of schemes we use are called counterdiabatic protocols. And essentially, if you're familiar with the adiabatic approach, which would be this evolution, the time-dependent Hamiltonian we see there, by introducing these counterdiabatic terms, by this adiabatic gauge potential, you can essentially shorten the evolution time, which renders into a shorter expression of the digital circuit, once digitized or taken to an analog device. The trick here is that obtaining this adiabatic gauge potential is not that easy. It's actually computationally really expensive, and there is plenty of people working in clever ways to approximate that adiabatic gauge potential. And this is where, let's say, we leverage our knowledge. This is one of the papers that we also released last year, where we made the comparison of a canonical adiabatic approach solving a 20 portfolio optimization problem and using DCQO, which would be the optimization version with CD protocols on first order expansions. And essentially you can see that rendering a distribution, which would be the blue line that is closer to the minimum energy state, is actually much more efficient, at least in terms of entangling gates. We can come up with this distribution that is much closer to the ground state than with a much more demanding adiabatic approach. So what I'm going to talk about is some of the work that we have been doing in the regime of machine learning. We're essentially trying to come up with ways in which quantum computing could enhance or help our customers in their machine learning pipelines. There are some hardware-specific approaches you can follow, like quantum reservoir computing or convolutional, quantum convolutional neural networks. But essentially, we try to identify those cases that could be easy to adopt by our customers. So applying counterdiabatic protocols to data embedding, to how you embed data, classical data into quantum state, that was one of the, or is one of the work lines we have. Modeling, so trying to come up with ways in which quantum computers can actually enhance the training of models is also something that we have seen 3D protocols can help in reducing the time and actually trying to come up with the same precision, numerical precision you could obtain by classical means. But what I'm going to talk about is the CD protocols applied to feature selection. One of the, I would say, big issues we find when we go to the industry is that you need to select, you need to distill, you need to reduce the amount of data you have. It could be due to different reasons. It could be due to privacy, it could be due to efficiency, but essentially this is a task that most of our customers want to evaluate at some point in their pipeline. So what I'm going to talk about right now is about some results that are not yet published, that will be published, but essentially some of the results that we have seen by applying these CD protocols. So feature selection is it's an easy problem, or at least stating the minimum expression of it is quite easy. Essentially, you want to maximize the information rotation on your data set by simply removing those features that do not contribute that much to a given target. So you can phrase it like the mutual information between each feature to the target. That will be the contribution, how much information they contribute with to the data set, let's say. And you can evaluate pairwise how much overlap is between different features. So essentially, if two features overlap a lot, you know that you can remove safely one of those without removing too much information. So if you maximize that thing over there, you will get the subset that contains the maximum amount of information restricted to a set of numbers. To a set of features, sorry. So if you switch the signs, essentially minimizing that function over there is equivalent to maximizing that thing over there. So in an ideal scenario, we would end up with our adiabatic protocol, the superposition of all potential selections. So once I select this feature, 0, I don't select that feature. You run it for a really long period of time, and you end up with a global solution. One of the issues, let's say, we find when we try to run this type of computations is that it's hard to get the actual ground state when you go to hardware. It's actually really hard to get that particular state with high probability. But also, in these particular cases, we are not interested in just the value, the set of features that maximize this function. We are interested also in suboptimal results, which we could somehow get from these evolutions as well. The main idea behind that is that we don't want, let's say, a single selection that will bias our model at the end. It actually could be that the one that maximizes the information is not the one that contributes to a more general problem or a general model once we model. Some features might be preferred on others. So if you have equally, let's say, energetically equal subsets of data, you may want to select one or the other because of some of the features are really hard to compute or are, I don't know, goes against some regulatory issues we may have in our particular use case. And there is always this component of a human in the loop. We need somebody that wants to evaluate the selection we have made. So essentially, we found that we don't need to provide the global optima, we just need to provide a subset of good options in this case, in this particular case for feature selection. So we started looking into different data sets, production grade data set, let's say, but these ones that I'm showing are more toy type of examples. If you go with the Iraitz data set, which is a 4-feature data set, it's not that complicated. You see the gap between the minimum energy and the higher energy levels. It's quite big. Let's say during the whole evolution, you can essentially be confident that you will obtain a good result at the end on the ground state occupation. If you scale it up to 13 features, you already see that there are some challenges there on the gap. There will be some transitions from ground state to higher energy states, which could be fine to some point, but we want to guarantee that at least the options that we're gonna get are in the lowest regime for this particular problem. So, I mean, we are also experimenting with larger data sets, but 13 seems to be already quite a challenging data set. By expanding different orders of this nested commutator approach, we see that all of them follow what we expected. The more you expand these city terms, the higher the gap is. So you are actually contributing to increase the gap and kind of easing the evolution. So you can shorten the evolution and come up with the ground state at the end. Interesting enough, some evolutions are counterintuitive. So if this is the occupation graph, if you look at the red line, is the occupation you will have for this evolution time following the adiabatic approach. And as you add counterdiabatic terms, you essentially see that it increases up to one point where no matter how much you increase it, you essentially reached the maximum you could get for this short evolution time. And kind of coincides with some of the expectations we had in previous works, where the approximation ratio, so the closeness of the distribution to the ground state, is not maximal, it's not 1 in the lowest evolution time, but it's in an order where you can still work and retrieve meaningful information from it. So once you have come up with these numbers, with these schemes, let's say the whole thing is where you run those. If you go to digital machine, analog machine, or you can leverage some digital analog approaches. In any case, this is still an application-specific feature and feature selection problem into a specific hardware you need to transpile it to. So the way in which you can take this evolution with the numbers you have come up with into this, let's say, digitized version, it really matters and could be really challenging to build. I will tell you a little bit on that afterwards. So for this 13 feature selection case, these are some experiments we run and that will be published in a short term. But essentially what you could see is that by these city protocols, we enhance really the peak that is closer to the minimum energy. That means that we can essentially take out of this quantum state that we get at the end of the evolution, the lowest energy states that map into suboptimal feature spaces that are good enough or that they contribute with a large amount of information. I would say that from this graph, the blue line is the adiabatic approach, the orange line is the counterdiabatic protocol with one city expansion. And what you can see is that even though we are interested in that peak that is close to the lowest energy, is the suppression of higher energy states. We know that our algorithms will focus in this lower energy regime, so we will remove a huge part of the search space, which contributes a lot into what we are aiming for. This is no variational approach. This is just one single, not one single, it's one circuit running for different shots, but essentially no variational approach. So you can efficiently run this and retrieve the results you want from there. Of course, if you are interested in the global optima, you can tweak these numbers and you can essentially iterate over it to get much better, a closer approach of this peak to the ground state. But it's interesting that this is done in a single iteration. One of the main challenges we find ourselves is building these schemas. So coming up with the right number for city expansions, coming up with the evolution time. So we essentially thought that this could be also helpful for others trying to approach these non-mainstream techniques. And we actually leverage this site that you can scan, you can go to, and you can pre-register so that our customer team will be in touch with you, will provide you an API key, and you can test this composition of CD terms. So you will end up having a Quasam expression of your circuit without going into all those steps for your particular problem. So you can start benchmarking, you can explore, you can see how it behaves for your particular problem, and of course engage with us and tell us when it works, when it doesn't work. So this is all I wanted to talk to you. You have also another QR code there to get in touch with me, essentially because we are still working in further improving our compression algorithms. We engage and we like engaging with domain experts in order to know when they become really, when they can really enhance whatever you have tested before. And also, I mean, we partner with main hardware vendors, but of course, if you are not in that list or if you're not familiar with us, please approach us. We are in the exposition floor as well, so you can reach and talk to us, talk to Daniel, our CEO, talk to Jan, our neutral atom expert, talk to Gernot, our chemistry expert. And if you want to talk to me, you can do it, or you can send me an email. You have my contact there. So thank you so much for attending.
Thank you very much, Iraitz. Well, we'll take a few questions. So someone asked if you could explain what is the difference between what you propose and the quantum annealing, for instance, D-wave method.
So from what I explained, quantum annealing, as long as you preserve the gap during the evolution, essentially you can do a really long evolution and end up having the ground state. The main challenge is that when you try to implement this on hardware, the evolution time you may require for really challenging problems could be really, really large and could go beyond what the qubit lifespan is. So by including these CD terms, essentially you can come up with a much shorter version that will actually fit into the qubit lifespan and actually do a quantum computing on that. So in those cases where we are not targeting, let's say, the global optima, but the suboptimal regime, we still are efficiently running on the qubit lifespan, let's say, and enhancing those optimal, so global optima and suboptimal states that are close to the global optima.
Thank you. And how sensitive are these protocols to error when you do the actual implementation, do you think?
Yeah, I wouldn't say they are much more sensitive, let's say. The benefit of these protocols is that they require much less operations. So the less operations you have, the less error you introduce. And then the mitigation you can impose on top of that could be a little bit more efficient than when you do a larger scheme.
Interesting. At the beginning, you mentioned like a reduction in the circuit depth of 200. How the baseline is defined?
So in this case, was a simple comparison of the number of entangling gates you would require to simply run the same exercise using adiabatic approach and using counterdiabatic approach. So the same, let's say, evolution time was required for both, and we measure the number of entangling gates that are required out of this schema once you digitize. So there is no baseline other than the comparison of the digitized, let's say, adiabatic approach and digitized counterdiabatic approach.